But let me begin with a little history. Marjorana, let me read this to you. This is from an introduction to an issue of Science recently, October 14, I think. Nearly 80 years ago, the Italian physicist Vigier Marjorana proposed the existence of an unusual type of particle that is its own antiparticle, the so-called Marjorana fermion. The search for a free fermion, free Marjorana fermion, has so far been unsuccessful. He, for example, suggested that perhaps neutrinos were Marjorana fermions. But bound Marjorana fermion-like collective excitations may exist in certain superconductors, and people have detected this, or so they say, and there have been a number of experiments about this. This is a very interesting elementary particle. It just interacts with itself to either produce itself or to produce nothing, energy. That's it. It's its own antiparticle. This is almost a mathematical entity. And in fact, we're going to see how it's related to fermions, regular fermions, and we're going to see how it's related to some more general issues. But you can try to imagine what this would be like. So the fusion algebra of a particle is the combinatorics of how it can interact. In this case, if you have many particles, then you would say, you look at the I particle and the J particle and see how they interact. They interact with some other particle or particles. That's the fusion algebra, the way they interact. In this case, the fusion algebra is very simple. P times P is equal to either P or star, P or 1. On the other hand, there's another kind of algebra that's normally associated with a particle, and that's the creation and annihilation operators for the particle. And I tell you, and then I'll explain to you why, the algebra for that's associated with the Marjorana fermion is given by the simplest Clifford algebra. That is, it consists of this is for two Marjorana fermions I've written here. A squared is equal to 1, but if you had another one, then B squared would be equal to 1, and they would anti-commute. All right? That's the creation annihilation or operator algebra for the fermion. So there are two algebras that are associated with it. Just so for an ordinary fermion, and I want to recall that for you, an ordinary fermion is associated with an operator which I'll call F, and a conjugate operator which I'll call F star. And one is regarded as the annihilation operator for that fermion, and the other as the creation operator. And those satisfy that their squares are 0, so we have no potency immediately here, and we'll come back to that later. And F star squared is 0, and then there's a commutator type relation, but it's an anti-commutator. FF star plus F star F is equal to 1. And this is posited by physicists because it's the exact analog of what happens with bosons and with the harmonic oscillator. If you started with a harmonic oscillator, but flip for fermions because they're just the anti-symmetry of the fermion and the Pauli exclusion principle. So the first thing, FF equals 0, is essentially the Pauli exclusion principle. So that's the usual algebra for a fermion. Now, the relationship of that with somebody whose star is equal to itself is in the next bit of algebra here. So suppose that we had A and B, so that A squared and B squared are 1, and that AB plus BA is equal to 0. AB is minus BA. And suppose that I define U to be A plus IB and U star to be A minus IB. A and B are invariant under star. They just stay the same. But if we take A plus IB, and I is the usual square root of minus 1 here, and multiply U by itself, you see that we produce a little algebraic machinery that produces a nilpotent. You see, A plus IB multiplied by A minus IB is A squared minus B squared plus I times AB and also I times BA. AB plus BA is 0, and A squared minus B squared is 0 because they're both equal to the same thing. And so U times U is equal to 0. and U star times U star is equal to 0. So the basic picture of that nilpotent that is giving a fermion in the usual picture can be thought of. You can think of a fermion, of an electron, as a combination of two Majorana fermions in mathematics. It has that pattern. And the other, the anti-commutation relation, I'm wondering whether there's a laser beam on this. There is. Little faint. The anti-commutation relation works just as well. See, you would have to do a little calculation, but let's do it as long as we're here. So I multiply these together, and you see it's the same as U plus U star times U plus U star. Why? Because the U squared is 0, and the U star squared is 0, so all I get are the cross terms, U star and U star U. But U plus U star is just 2a, so I get 4AA, and that's just 4, constant. So the other commutation relation works out as well. So this is the simplest instance of the relationship between Majorana fermion and fermion, and it's also a very interesting way to think about how a nilpotent operator arises, how those nilpotents that we've been talking about for the last 2 days arise. You can make a nilpotent like that, and it shows you that nilpotent algebra and Clifford algebra are tied right up with one another in exactly that way. So this is interesting mathematically, but it also is very suggestive that perhaps under certain circumstances an electron could be thought of as two other particles, and we'll come back to that. But what I wanted to emphasize here is that structure which is in physics. And now I'm going to take a digression that walks away from this for a while and then comes back. So the next part is motivated by G. Spencer Brown's notion of a logical particle that interacts with itself to either confirm itself or cancel itself. And this interaction combined with recursion leads both to matrix algebra and to the very elementary mathematics of the Majorana fermion. So I'm going to take a mathematical digression here, but the mathematical digression is one of great generality because what I'm thinking about is the nature of a distinction. And if I'm thinking about the nature of a distinction, then I'm thinking about what it is that can be observed either in our thinking or in our observing of the world at all times, every time, all the time. Whenever you are making any kind of observation, whether it's thinking of your own thought or examining what you see in front of you, you are always involved in a distinction. And when you are involved in a distinction, it means that there is present an observation and an awareness, and there is also present some kind of duality that says that is there and I am here, or this is there and the other is over here, and they are distinct from one another. Some distinction is being made that tells you that something is different from something else. But along with distinction come recursion. The fact that you can repeat, the fact that you can repeatedly identify something. It's part and parcel of having a distinction at all. So, for example, I look at the cup over there, and I look away, and then I look back at the cup, and there, it's still there. And as I'm looking at it, it retains its cupness all the while. And if you think about what you're doing there, and I'm talking about the properties of ordinary, what the physicists would call macroscopic observation, then you see that there is, if you try to describe it mathematically a little bit, you see that there is some kind of operator, which is the operation or operator of viewing it, and that operator gets an invariance. I get cup and then I get cup again. If I got cup and then I got squirrel and then something else, then I would be well looking at a changing process. And of course, we're familiar with looking at changing processes. You can look into a waterfall, and then you find that you're, at one level you see the whole waterfall as a whole, and at another level you are watching the individuation and process and changing, continually changing thing that's going on. So So there are many examples of this, and there's a nice concept that's useful for that, which I call eigenform. And an eigenform is just a fixed point of some operator. All right? And you can make eigenforms. Let me go to the next slide and then come back. I can create an eigenform, for example, spatially. I can create an eigenform out of this nest of boxes, because I think of this nest of boxes as something which is invariant under putting one more box around it. If I put one more box around this, it has the same form, approximately the same form, since there are only finite operators, and how they might be produced. In the case of the box example, it's a nice example, because the operator itself, putting a box around it, actually can produce the eigenform for itself by composing itself with itself as many times as I like until it begins to become invariant. So one way to get a fixed point in general is to take some operation and then keep applying it to itself again and again and again until there is an invariance that comes about from it. So you can make forms out of nothing in that way. And then I'll come back to this slide. Whoops, not that way. When you have the circularity of observation, like a universe observing itself in Wheeler's picture, or a form that is pointing into itself in this picture, or to give a more specific example, a linguistic form that fits into itself, like this one. I am the one who says I, and the operator in this case is O, the one who says, and I is what's invariant under O. Right. There are lots of linguistic forms of that kind. And if you start to think about it, then you realize that when we talk about the macroscopic world of observation, you could take on the notion that what you're talking about is the world of eigenforms. That you are examining things that are invariant under certain operations that you have available to you. So that's the notion of repeatedness in experiment, for example. And if the form that you're observing is the placement of a needle in a meter, it's exactly that, but in a very specific form. If what it is who's in the room or recognizing another person, it's harder to quantify. But we live in that macroscopic world that we live in is the world of eigenforms. I also chose Wheeler's self-observing universe because it raises very nice epistemological questions, as you know, that he raised. He said, well, there's the Big Bang, and the universe evolves, and eventually becomes capable of observing the evidence from the Big Bang. And then he said, a phenomenon is not an actual phenomenon until it is an observed phenomenon. And so, in what sense is the universe actual before this observation or this collection of observations begins to take place? In what sense is the universe actual before it becomes eigenform? That was Wheeler's question, which I won't attempt to answer. But I have modified Wheeler's self-observing universe this way. And you might wonder, why have I done that, other than that it's amusing to look at? Because a knot is a very interesting kind of form. A knot acquires its form from its context. If this knotted tube were in nothing, it wouldn't be knotted. It's only knotted because it's embedded in two-dimensional space and self-relating in a certain way. Without that, it has nothing, it has no knottedness. The knottedness has to do with the context in which it lives. And whenever we talk about anything, we put it into some context. And again, there's a paradox for Wheeler's universe, because the universe is supposed to be everything. And so what is the context of the universe except itself? Let's go on. I think I already explained this slide, except for one thing. You can imagine building up an eigenform like the infinite collection of boxes, by putting one box around another box around another box. But if you think of that, that's a process and it's going on in time, like this, box, another box, another one, and so on. So there's a temporal process, or there's the spatial end of the temporal process. And when you think about this kind of thing, then you see this duality between space and time in a very concrete way, that you may imagine that the space is being built up through the process, or that the temporality is the unfolding of the spatial structure. And so it's good to have that around. We'll come back to it. Now, why do I say that I want to talk about Spencer Brown's calculus when I started talking about Majorana fermions? Well, it's because of this striking thing here. Here's his calculus. I'm introducing it to you without explaining it. There's a mark, and this mark, oops, sorry. There it is. I got the right button, yes. This mark has two ways of interacting with itself. If it's inside itself, then the two marks concentric to one another cancel and produce nothing. And that's a literal nothing in the plane. That star is an empty, is just an empty placeholder. I might write 2 marks equals blank, if you like. And 2 marks next to one another produce a single mark. The mark can relate to itself in 2 ways. It's either next to it or it's inside it. And when it's next to it, it confirms itself and just gives rise to itself. But when it's inside itself, it negates itself. And so if you start staring at this and wondering, well, what was this supposed to be? You realize, well, it's acting like the negation operator, right? Not is no nots at all. And indeed, that was the intent, that this would act like a negation. But this is also like a negation operator, but in a different mode, and we'll have to explain that. In any case, it was and is a way to redo logic at a slightly deeper level than the usual Boolean level, and it produces this logical particle, and the logical particle is exactly a combinatorial Majorana fermion. It interacts with itself to produce itself or to produce nothing. So, so that's why I wanted to bring this into the discussion. But the epistemology of this is that the mark is seen to make a distinction. So the mark is meant to stand for the act of distinction. As such, you will do to it what you usually do to symbolism. You put it out there and make another distinction. And if you put it out there and made another distinction, then it's just a mark on the screen. But if it's your mark, if it's the mark you made, if you own it, if you're the producer of it, and you are the producer of it since you're looking at it, then it's also an extension of yourself, or it is yourself in some sense. And then it really does stand for the act of distinguishing. And then these are interpreted in various ways. One way of interpreting this is that that fit together do each other in. Like if I really have something that fits something else, then basically everything disappears nicely. Or another way of thinking about it is that the mark is an instruction to cross a boundary. And then if you cross the boundary again, you can be back where you started. And on the other hand, the mark can be seen to name the space in which it is drawn, in which case this is 2 namings of the space in which it is drawn, and 2 namings can be regarded as a single naming. Those are some of the interpretations of this in the logical mode, or the linguistic mode. So as I say, in the formalism, the mark is seen to make a distinction. The formal language of the calculus of indications, the calculus of this, refers to the mark, is built from the mark. The language that uses the mark is inherently self-referential. The mark stands for a distinction, and it is a distinction from the point of view of the one who uses it. This calculus writes itself in terms of itself. And then I give you the very last lines of Spencer Brown's book, Lost Form. this is the last line of the book. We see now that the first distinction and the observer are not only interchangeable, but in the form identical. And I don't mean that to be particularly mystical, as I said. I mean that to discuss the fact that when you have a distinction, you're involved in the distinction. And when you have an observation, you're involved in the observation. And that one should keep that in mind when thinking about physics, because it's very easy for us to make a mathematical model of observation, projection of some sort, and then decide that the observer has been removed from that and that it's all just somehow in the mathematics or in the formalism, but it truly isn't. And so this itself is a formalism that allows you to keep remembering that and perhaps compare what goes on in such a formalism with what goes on in more complicated ways of thinking about things. Now, I'm about to embark on a little more complicated thing. Now, I would like a model, a geometrical model, of how I could think about two entities that interact to produce themselves or to cancel. And here's a geometric picture that I like. So now I'm playing around with the surface here. I have a surface here, up there. I have a little pair of pants surface, right? Upper boundary and lower boundary. Pair of pants are upside down. The two circles interact by coming near one another and going through a singular saddle point right here and turning into one circle. If you were to look at it temporally by slicing it, you would see two circles that come in and touch, and then they share a little bit, and then they untouch, as it were, canceling what they share and turning into one single circle. In the other picture, I have them concentric to one another, and one of them grows larger until it just touches the other one and cancels it out. And if you trace that with a surface in space, you would see this, these two tubes that are, one is inside the other like a kind of a vase, and a little bit of a curve at the bottom, where at the very bottom there's a little tangent curve, and that's where it disappeared. So you can think of abstract strings like this interacting and being Marjorana fermions, if you like. One picture. You see that is the same as the logical particles picture. You have two circles next to one another, which can combine to give you a single circle, and two circles concentric to one another, which can cancel each other out. And then I remind you also, we're playing around with the fusion algebra, right? I remind you that we could write P interacts with P to produce either nothing or P, and plus now means nothing. Plus means or. And that may remind you of a quadratic equation from long ago. X squared equals 1 plus x. And it has the same formal properties. So that if you let Marjorana fermions interact with one another more than once, you will pick up Fibonacci numbers. You see, p squared is star plus p, but p cubed is p times star plus p times p. But p times p is star plus p, which is 2p plus star. And if you then multiply by p one more time, you'll get 2 stars plus 3 p's. And then you get 3 stars plus 5, and 5 plus 3, 5 plus 8, and so on. 3 and 5, and 5 and 8, and so on. You get the Fibonacci numbers. So sometimes people call this particle a Fibonacci particle for that reason, that multiple interactions give rise to Fibonacci numbers of results. We'll come back to that too. And now I'm repeating myself. The circles interact either way, and it fits with the laws of form picture. But I'm interested in the epistemology of this, so I want to digress a little bit. If you were just doing logic, you would have the following question. Could you somehow make a Marjorana particle, if you had the idea of making a Marjorana particle, out of negation alone. We just did, but what happens if you're thinking in the usual mode? Well, Wittgenstein was thinking about this. He was thinking about the question, what is the relationship between his mirrored reality of the world in the Tractatus and the world? He forms a description of the world and talks about how the world is mirrored in his logical descriptions. And he says things like this. That, however, the signs P and not P can say the same thing is important, for it shows that the sign negation corresponds to nothing in reality. And then later, how can all-embracing logic which mirrors the world use such special catches and manipulations? Only because all these are connected into an infinitely fine network to the great mirror. The limits of my language mean the limits of my world. The subject does not belong to the world, but is the limit of the world. And I think that it was things like this that eventually gave him enough problem so that he changed his way of working with language and epistemology in his later years. Because, as you see, he has this mirror, but it's quite distinct from the world, and negation isn't in the world. But in this other point of view, negation has fallen into the world as a distinction itself, and interacting with itself to reproduce negation, or to reproduce or. Because you can think of this as the negation of negation is nothing at all, and this is A or A is equal to A, but they live together. They live together this way. And we can have our languages and our descriptions contiguous with the world and not separated from the world. Just a side remark, how is it interpreted for logic like that? This is not A. A next to B is A or B. This is like what we were hearing in the last talk where you remove the plus and you get 55. Here we are removing as much as we possibly can in the symbolism. And the mark is true and the unmarked state is false. That's the way you interpret it for logic. And I just thought I would also illustrate the formalism for you a little bit, since these would be interacting Marjorana fermions in some form. You see. That's allowed, right? 2 can become 1. But these two guys could cancel, and these two guys could cancel, and these cancel, and we ended up with nothing. Or in circles, these two guys cancel, 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 down to 1. Or it could build up out of nothing, out of nothing, out of nothing. And to shift to another part of the picture of fusion of Marjorana fermions. This is somebody's dream. It comes from a Scientific American article, and it's a specific dream. It's the dream that you might be able to have collectivities of electrons in the form of vortices in a two-dimensional situation like the quantum Hall effect, and that you would be able to manipulate the way in which these collectivities move around one another. Because when these collectivities move around one another, at least theoretically for that bit of physics, they get a phase change which is not just plus or minus 1. And consequently, you get a very non-trivial braiding. And it also illustrates the space and time relationship of braiding. I have here a braid, but you can see that this braid in the imagined picture is the result of, maybe it's the result of the puppeteer just holding those strands, while the vortices, which are attached to the braids, of course not really, are causing the braids to wrap around one another over a period. And so over a period of time, these braid strands are getting braided by the fact that the vortices below them are moving around. Or it could be the other way around, that the puppeteer is somehow causing the vortices to move or using his braid. Either way. It could be an observation or it could be an action. But the idea was, and still is, that perhaps we could control those quantum states in vortices in a flat, very cold plate. And it turns out that the vortices in some phases of the theory of this, at least, are Majorana fermions. And it turns out that Majorana fermions in that kind of context can have very non-trivial braiding. These are collectivities of electrons, and in the theory of this, they have very, very non-trivial braiding, and you might wonder how this looks. So I thought I would just give you a little picture of that. Now this is a very condensed picture of this, and maybe I should draw something on the board to show you what's going on with part of it. If we have, oh, maybe we don't.
Oh, I asked for them, but I guess.
Do we have any crayons? No crayons? Markers. You don't have to run off and get them. I'm fine without it.
Oh, okay. I'm sorry.
If they're not in the room, let's forget it. Okay, so we just look at my board. The problem with this slide is it has too many things on it, but I wanted to show you something interesting that it has, and that is right here. Just look at this. This little two-stranded object here, which is a piece of some mathematical formalism, and I'll tell you what goes on in a moment, it actually means two parallel lines minus a factor times two turnaround lines. But without drawing on the blackboard, I couldn't show you why I am so interested in things like that. But the idea is that then, when you put them together like this corresponds to this particle interacting with this particle to produce this particle. And the rule is that you have to connect the lines and have no free lines inside, all right? And then you see there are two basic ways in which you can do that. Pitchfork little connections. You can do it this way, taking two down into this one and one going around. Or you can have them both going back around. Or you can do something else. You could have a fourfold die, but I didn't allow a fourfold die in my situation. That would be another particle altogether. So we'll forbid that. It turns out you can forbid that by using the mathematics at a certain root of unity. And then these are the only two interactions that are possible. And you see these are exactly Majorana fermion type interactions. These two interact to produce this, or these two interact to produce nothing. A little like the simpler one with the concentric circles, but in this case, little lines that are braiding, that are really meant to be braiding lines, but they get to turn around a bit like that. So those are the basic interactions in the model, and then it turns out that there is braiding in the mathematical model. That is, you can have a bunch of these things and strands coming down, and if you twisted some of these strands, those would get expanded into various combinations of sums of lines that either are going down or turn around. And you can calculate how the braiding works, and you end up with a mathematical model of these particles interacting and braiding one another, and you get phases that they interact with, like these, certain roots of unity, certain phases, and then there are some other technical aspects of the model that have to do with changing basis and when you let them interact, because, well, that part I won't bother you with. I just wanted to show you the sort of surface structure of what the so-called Fibonacci model looks like, which can produce unitary transformations that come from braiding of Majorana fermions, like the collectivities of the electrons. So there's a simple mathematical, simple for topologists mathematical model of how to do this braiding and get unitary transformations. And then I need to say something else to you about what the background of that is for just a second. I'm talking about quantum computing here. I'm talking about making the phase changes that those collectivities undergo, reining it in so that it could be used to compute something. That's a simple quantum idea from quantum theory that people have been studying for a long time. But it's a very simple idea. The idea is, well, a quantum process is a unitary transformation. Maybe you can use finite dimensional ones, and that would make things easier. But if you can imagine some mathematical problem that you would like to solve, if you can translate that problem into a unitary transformation whose statistics, when you observe it, will give you the answers to your mathematical problem, then that's a quantum computer. Because what you can do is you can imagine realizing the unitary transformation, making it actually happen in the world, and then you have this black box, which does the unitary transformation, and you keep observing the end result of the black box over and over and over again, getting the statistics. And if you designed that unitary transformation in such a way that it was actually computing the math problem you had in mind out of the statistics that you would see, then you would get the answer after a while. And it turns out you can do that, and you can, for example, factor numbers in principle faster than classical computers, according to Peters, which is, in fact, a design of a certain unitary transformation whose statistics you observe. So all you have to do is build a computer to do that. You have to build the actual physical apparatus that does this quantum process. And of course, that's not easy because of decoherence. And so no one has really quite yet accomplished this aim except in the lab for a very small number of quantum bits. And certainly not managed to factor large numbers yet by using Shor's algorithm. But then there have been many different schemes for hopefully doing that. And one of the schemes that people are interested in, for example, the Microsoft people are interested in, is using the quantum Hall effect and the collectivities of its electrons and the kind of thing that I'm describing here to control that and use that to produce the unitary transformations that would be at the base of a quantum computer. And there are other schemes, of course, as well. And while it may still be a long time before people make real quantum computers, the mathematics of this is very interesting. And the reason I'm bringing it into the theme here is because you see that you start with this very elementary idea of a Marjorana fermion, which is so close to the notion of just bare distinction that it's worth thinking about epistemologically. And it does have its possible realizations. And those realizations are very closely related to topological things. Here, the description of how it's related to braiding is a little complicated, and I kind of eliminated it from the discussion, except to give you a little bit of a hint about it in this slide. But we're going to see braiding on the other side as well in a few minutes. Just checking the time. In a few minutes, we'll see that braiding is also related to the creation annihilation algebra for fermions. So braiding occurs on both sides. That's another reason that I'm very fascinated by this, that braiding is very close to the notion of a fermion, however you take it, whether you take it in terms of the way they interact, or if you take it in terms of creation and annihilation. We're going to see topology there either way, but I'm just running ahead of myself with that. So as I say, this Fibonacci model, the one I just indicated to you, yields a braid group representation that is universal for quantum computation. That is, the braid group representation, the phase relations that are coming out of that, are strong enough so that you can build any unitary transformation you want, finite dimensional, up to approximation. So it's as though underlying all of quantum mechanics in some sense up to density is topology, braiding, that you can at least say that mathematically. Of course, it would be an entirely different thing if I could show you how, by looking at the universe in an appropriately fundamental way, we would see that all the processes of the universe are coming out of braiding. I don't know how to do that, but it would be fun if I could, right? Maybe that's possible. But this is a mathematician's construction, that you can make these braid group representations dense. Well, there's our dream again. Now I'm going back. I want to show you something else. I want to show you how algebra, matrix algebra, the square root of minus 1, really all of matrix algebra, in particular the little Clifford algebra we started with, all of that emerges very naturally out of the recursion or the eigenform in its most rarefied aspect. So here's the eigenform again, just iterating a transformation on itself. But I want to turn it into something a little more numerical to look at. So I'm going to let it be plus and minus 1. And I'm going to replace the cross here by minus 1 over x with malice aforethought, all right? Because now I have a favorite mathematical eigenform in front of me. If I take the transformation, t of x is minus 1 over x, then I is the solution to that, right? Minus 1 over I is I squared is minus 1, right? Okay, so I is a nice eigenform. And on the other hand, if you think of it temporally, if you keep applying it to itself, well then you could have started with 1, let's say. The transformation is t of x is minus 1 over x. You could have started with 1. And then minus 1 over 1 is minus 1. And minus 1 over that is plus 1. And minus 1 over that is minus 1. And so I get an oscillation. The oscillation never arrives at the square root of minus 1. It's just always oscillating back and forth. The square root of minus 1 is a leap that you took to a solution to the eigenform. And it is like I am the one who says I, in that if you try to iterate to produce the I, you won't get there. Lots of eigenforms have the property that they are simply the solutions to the equation, but you don't get there by approximating, or at least no one knows how to get there by approximating. The well-known question of is it possible to produce an intelligence or a consciousness by somehow iterating the process of producing machinery is similar to trying to produce I by applying the one who says to the one who says to the one who says, and if we apply it infinitely often, we get a solution to the one who says I is equal to I. But did it actually produce what you wanted? Somehow similarly to the solution, and that's what people said, they said, well, there is somebody there, square on the other hand, in this case, when we have the oscillation, you could somehow out of the oscillation itself, we get the I, but we'll have to be more intelligent than just saying that the oscillation itself is the I. We'll have to figure out how to multiply. And we do that. Well, there are two ways to look at this oscillation. One is that it starts at minus equals plus, and the other is that it starts at plus equals to minus. So that's a suggestion. Maybe that's I and its conjugate. I did this too quickly on this slide because I went from plus and minus the A and B, but if you could bear with me, because they don't have a blackboard, make it more powerful. I'm thinking of the A and C as the plus and minus. I'm introducing the operator that shifts the B and the other, the AB and the BA. But I'm going on one side or the other. So if you meet this operator and it's put on the other side, just as though you temporarily sequence the sequence. The sequence is going plus minus plus minus plus minus. And if you push the operator theta across the other shape, so to the other phase of it, it's as though it's shifted in time up to one select. So I'm introducing a temporal shift operator, which I'm calling A. Okay? And then I'm going to do two things. We'll see what happens in a moment. I'm going to think of combining waveforms like this, discrete waveforms or discrete processes. So if I have these as CD, CD, or CD, then they combine by just taking A and C and B and C and B and A and C and B and B and A and C and B and like that. On the other hand, I could find on my equation 1 minus 1 A. And now watch what happens. If you say 1 minus 1A, this is temporarily sensitive now. If somebody else needs it, you get time shift because the data is a little bit of temporal process placed in the algebra. To put them together, and watch what happens. You look at 1 minus 1 times eta, and 1 minus 1 times eta. And eta shifts across the 1 minus 1, and the 1 minus 1, and the 1 minus 1 turns into a minus 1, 1. Because that's just like if you place combined, you do minus 1, minus 1. And the etas, if I'm assuming that if you do eta twice on backward to start it, because if you shift it 1 minus 1 and then shift it again, so that's where you work. So eta squared is equal to 1. And we have constructed the model out of the oscillation, out of the attempts to iterate the process. But we got that by imaging time into algebra in this way. Eta is temporal, and this is a temporally sensitive entity. If something comes up to it, it can get shifted by data, and shifted if you think of it as a process in time. So what happened was, you have these two temporal processes, the 1 minus 1 process and the minus 1, 1 process, and they're fitting like this. But we have an eta in between, and because of the eta, they get shifted by 1 minus 1. And then the minus 1s are just meeting one another, so the plus 1s, instead of the plus 1s meeting plus 1s, and the minus 1s meeting minus 1s. They go out of phase with one another, and squared equals minus 1, I squared equals minus 1. So I squared equals minus 1 if you make a model of this kind. So what we constructed that first, we constructed that first separate algebra. Here is E, and E is not E itself. It's not temporally sensitive. And when you square it, it just multiplies its constituent parts and gives you eta on the other hand. E eta on the other hand, that's the I. There's a mistake on my slide. The eta was supposed to shift over. The eta was supposed to shift over to the other side, and it didn't on this slide. Altogether on this slide, the eta was supposed to be on the other side. The eta is minus eta e. Sorry, it's not accurate. It's collected at the So there's our quick for that. E squared equals minus eta e. And in the Clifford algebra, you take this product of these two squares from the other one. There's minus e. So what you see is that in this first line of the square root of minus 1, it's happening in a non-computed situation. The square root of minus 1 really fundamentally is part of a non-computed situation. It's only about education and the history with the thing that we thought that it was a computed situation, and then there were later developments of non-computed situations. The square root of minus 1 is always part of this commutative situation like this, from this point of view. If we think of those as temporal and spatial elements, then you think of the fermion that you would create out of them as combining the spatial nature of this and the temporal nature of this into one fermion. But that's all just mathematical talk about. It is combinated. These are fermion operators now. And we arrived at the Marjorana in a Clifford algebra in a perfectly natural way by thinking of discrete process. This is where we should take the break, or do we go to 12 and take the break?
So we were originally down to go to 12.
All right, so I'll do 7 more minutes and then take the break. So at this point, you see that it's not just the square root of minus 1 that has emerged from the structure of the oscillation, but the non-commutative algebra of the split quaternions. That's another term for E eta in the algebra they generate. I'm going to use this as an excuse to follow this over to the Dirac equation, and we'll do more. But we've also uncovered a source of matrix algebra, and it's worth seeing what I mean by that by re-looking at the formalism again. I can form in this arena that I've constructed for you of waveforms and waveforms with little temporal shift operators on them. I can form sums of them. So I can form sums of AB and things of the form C d eta. And I say that, in fact, this corresponds to a 2 by 2 matrix, just like that. That's exactly what it corresponds to. And the algebra is exactly the same as the algebra of 2 by 2 matrices. Now let me check to see whether I had a better slide for that. No, so I'll have to ask you to visualize something. If you believe that top part of that slide, then you should imagine what happens if A and B are 0 and C and D are 1, which means 1, which just means eta itself. Where is eta itself? It's A and B are 0 and C and D are 1. The matrix, the familiar matrix, 0, 1, 1, 0, right? That matrix. That matrix is a permutation. It permutes two things, right? It squares 1. So that's exactly what eta did. And then if you think about what I've called AB, you see that I'm calling AB the standard diagonal matrix. And what about the square root of minus 1? Well, the square root of minus 1 is when C is 1 and D is minus 1 and A and B are 0. And that would be a 0 here and a 0 here and a 1 here and a minus 1 there. Right? Anti-diagonal matrix with a 1 and a minus 1. Well, you're also familiar with that. That's a square root of ways to represent the square root of minus 1 in matrices, right? And now you're looking at it in a different way, though. You didn't think before, unless you were thinking about this interpretation, that the 1 and the minus 1 in the anti-diagonal of the 2 by 2 matrix that represents the square root of minus 1 is the plus-minus process that lies behind the square root of minus 1. It's actually there. So one way to think about this is we reinvented matrix algebra. And indeed, in fact, we can reinvent arbitrary n by n matrix algebra in a similar way. And I'd be happy to talk about that, but not right now. So that means that 2 by 2 matrix algebra, which is all we're looking at here, can be thought of as a kind of species of hypercomplex numbers where you have an eta squared is equal to 1, and eta applied to anybody is the same as eta on the other side applied to its flip, where you flip the coordinates. That's a nice hypercomplex number system, very non-commutative, and full of structure. Just that. You can do a lot with it. So that makes interpretation for matrix algebra. Here's an example that you might want to think about. We can represent a point in space-time as a 2 by 2 matrix, t plus x, t minus x, y plus iz, where I is already in there as a commuting I, and y minus iz. You can think of this in terms of what I just said, and then the spatial part is the part that corresponds to the first part of my decomposition is the t plus x, t minus x, where these two have been displayed together, and the I is over here on the other side. So you could think of this as having to do with a process, and the other one as having to do with imaginary values on either side of the process. There are lots of metaphors that are associated with representing a point in space-time this way. And in this, you'll notice that we have the Pauli matrices, and many other simple matrix systems are coming out naturally here. I like to think of the metaphors in terms of this kind of a mandala, where you have process and form instantiated together in that way. So to summarize, we can regard E and eta as the fundamental pair of Majorana fermion operators. It's a formal correspondence, but it's striking how the fermion algebra, Majorana fermion algebra, emerges from an analysis of the recursive nature of re-entering distinction, and the fusion algebra for the Majorana fermion emerges from the distinctive properties of distinction itself. We've seen how the Clifford algebra emerges, and that the mark embodies the fusion algebra of the Majorana fermion. I do think at this point this is a good place to stop, and then we'll continue on a little break. Yeah.
Take somebody.
I was thinking about the word distinction that you used. Do you know about Bentley and Bentley's book called The Knowing and the Known?
No, I don't.
Okay. Bentley and who is the educator? Forgot his Dewey. Dewey and Bentley in 1949 wrote The Knowing and the Known, and they have about 60 distinctions, over 100 distinctions in self.
Fundamental. They think are quite fundamental. Huh?
Well, they're developing a theory of knowledge.
Yes.
But some of the initial remarks that you made reminded me of their work. That
would be inevitable.
They use distinction because they don't want to use the word duality, and they insist they don't use duality or dualism.
I think I do the same, because I don't want a distinction to be only a duality. It can be adjoining just as well as a separated.
That's part of their definition. Now, the history of that includes Arthur Lovejoy at Johns Hopkins University, who wrote in 1930 the case against dualism. There was a move. Okay, I'll talk to you about that later. It's a long history.
Well, we're in the break. Yeah.
Okay,
people can get off.
Okay, so what Lovejoy pointed out is that Dewey and Bentley were Americans. They were influenced by a German philosophy, and who rejected concepts of duality and dualism. So he wrote why Dewey and Bentley in particular were against dualism, and then they came out this book in 1949, about 20 years later, on their theory of distinctions, not dualisms. But they argue two distinct things. But your theory seems to fit the initial part of it on self-reflection, their definitions.
It'd be interesting to see what they collected. If you start collecting, you say, well, I'll think about fundamental distinctions, whatever is fundamental for me, and then you start writing them out, and you see, oh yeah, right. Some of the things I do are really fundamentally related to this distinction or to that one. And it depends on who you are and what you do, what you will end up with. You'll end up with a list of about two. Yeah,
that's essentially what we do.
Yeah.
I just wondered, I was interested in this I am the one who says I as an example.
Yes.
If I interpret it, then we're either using a different meaning of the I in both cases. Is that something?
Yeah, it's a linguistic example, so there can be slides of meaning, of course. Not only that, right? You mean even on the two sides of the equation, I, the one who says I, by the time it's reached the other side, it's become the slightly more objective I, and the one that I spoke at the beginning is really referring to me. Right? I am the one who says I, and I has become weaker in the second part, in the way we usually speak. And then also, it isn't necessarily me, because you can say the same sentence, and then it refers to you and your I.
Well, more distinctly, in one case it refers to me, I am. In another case it refers to the sound. Totally different. So how I'm just wondering to what extent are
this is part and parcel of what happens in the linguistic situation. I think it's a good example of how, you see, it's so easy for us to slide from, well, I'm interested in physics and I'm going to watch the way the things work in the world, and it's my observation, to I let an instrument do it, and I get an indirect answer about what happened, or or I just work with the symbolic nature of it, right? That slide is even there in just talking about the eye itself.
Right, right.
Yeah.
So
you can't be doctrinaire and say it must always be that it's highly personal. You can't, right? You have to allow this kind of moving back and forth.
That's what you call the distinction. That's what you call the distinction.
I call a distinction what occurs for an individual when he finds that something is distinct. At first, right? Okay, at first. But then some distinctions have been agreed upon by us, right? It's not just solipsism. You and I agree that a circle drawn in the plane makes a good distinction between inside and outside, and then we can discuss the properties of inside and outside, or that the numbers, the standard numerals, can be used to represent numbers, and we exchange them, and we allow them to be printed and exchanged, and other people to use them, and it gets away from us, right? But it has to eventually come back to the individual who can still make the distinction in relation to that. Right? I set the computer to proving that 2 to the 137 minus 1 is prime.
Still working.
Yeah, and it says yes, right? And in order for all that to be meaningful, I have to know something about the whole process that I've allowed to happen automatically outside myself. I have to know something. So you're always led into this search for how much do you actually know about what is purported to be a distinction. It's a science. It happens in science all the time.
well, that's what I was.
By the time you're hungry enough, you can leave the room. Okay, so a couple of things came up in discussion that are probably worth mentioning. I don't think I have to go back to the slide, but you remember in a very early slide, I wrote as an example of an eigenform, I equals O of I, or I am the one who says I. And it's a good linguistic example because you will have noticed by now, if you're thinking about it, that the meaning of I in the left-hand side of this statement is different from the meaning in the right-hand side, right? So it's true that at the symbolic level, you're using I and I, but even when I express it, right, if I say I am the one who says I, I'm speaking from my personal I, but by the time I got to the other one, I'm referring to the symbol I. So that happens. And you could compare, and another one that I like along the same lines, and we might take a look at it, is a statement of Who I Am by Heinz von Forster, the cyberneticist. And he says, I am the observed being between myself and observing myself. And this is very interesting. I'll just repeat it again if you've never seen it before. It's a nice recursive statement. I am the observed link between myself and observing myself. In that case, I think all the references to self are references to honest references to self and not to symbols for self. So this has a better form than I am the one who says I, but I am the one who says I is very interesting and concise. The other thing that is interesting to look at is the way I constructed the square root of minus 1. If I was willing to be a little more slippery about symbols and algebra, because I could have said this. I could have said, by I want to mean the process, plus minus, plus minus, plus minus, plus minus. But I recognize that it's a temporal process, and that in order to pin it down by, say, observing it, a certain amount of time is required. And if I then did it twice, the second time I observed it, the time would have slipped along a little bit. And then the temporal operator that I put in would have happened out of the physical process of observation. So you said you did I, and then you did I again, and what you got were +1 the first time and -1 the second time because of the slippage in time. Of course, it didn't have to be exactly that much slippage in time, but that's what I created with the temporal operator. It slipped a little bit, and so it ended up being, I ended up observing plus, and then I observed minus, and so I got minus total, right? And I equaled minus, not plus. It's only with the perfect synchronization and no time that you would get plus and plus, or minus and minus. So, so that slippage is something that we engage in a lot when we're speaking in language. Certain kinds of precise or relatively precise slippages that form the meaning, that are related to our ability to extract meaning in language. If one were to try to formalize all of that, it would be very complicated. What happened in that definition of I is that I'm taking a little bit of that and formalizing it, but it's a particular one that I wanted to do for the sake of physics eventually, but earlier had thought of doing just because it was there. If it was physics, it would be the story I just told you. I'm thinking of discrete observation, and I have things that I'm observing, like position and velocity, all right? And I have a clock that's ticking. And I'm assuming that any operation that I do requires one tick of the clock if it's a velocity measurement. And if it's a position measurement, I can do it quickly and I don't require a tick of the clock. Position is spatial and velocity is temporal. And now think about that for a moment. I observe the position and then I observe the velocity. Okay. And the position is the position right now, and then I get the next position minus the previous position to get the velocity and take the difference, divide by the change in time. What if I did it? But I wanted to point out to you that that same thing could be resolved algebraically by a temporal shift operator, just like the one I made for I. I is a simple discrete process. And that's what I do, in fact, to make a kind of calculus of discrete measurement. And it's interesting to do that because you see how non-commutativity comes into the elementary physics even before or to the side of quantum considerations. It's just there out of the interrelationship of time and space and measurement. Okay? Maybe we come back to that. Now I'm getting back to this recent work about Majorana fermions. If you had a row of n electrons, mathematically it looks like 2n Majorana fermions, right? Each electron is a pair of fermions, A plus IB, right? It would be like this. This is what Kataev wrote down in this almost first paper on this kind of thing back in 2000. So he says, I have a row of electrons, but each one is to be thought of as a pair of Majorana fermions. And he wants to think about how this would behave. And that's all I've shown you from his paper. I'm just showing you a couple of papers. Oh yes, that's right. There are two parts to this picture. So on the one hand, you may have this situation, but on the other hand, the Majorana fermions from adjacent electrons might pair with one another. And he suggests that that's related to, perhaps in some situations, might be related to Cooper pairs of electrons, and does some analysis of how these systems would behave, hoping to use them for possibly quantum computing. Another paper that's very interesting, these are papers that are on the archive, you'll find them. I can put this slideshow up on a Dropbox and give you an address for it if you're interested in getting references. This is a very nice paper, mostly incomprehensible to me, but I managed to extract some things to play with from it by Ivanov, also around 2000, and he's thinking about the braiding of the fermions. I'll talk about the braiding. And then here's a kind of recent summary of things, which is a little picture. So you get a little picture. This is from the wiki on Majorana fermions. So in superconducting materials, Majorana fermions can emerge as non-fundamental quasi-particles, which are more commonly referred to as Bogoliubov quasi-particles in condensed matter. And this becomes possible because a quasi-particle in a superconductor is its own antiparticle. Majorana fermions in superconductors were observed by various experiments. Mathematically, the superconductor imposes electron-hole symmetry on the quasi-particle excitations, relating the creation operator at energy to the annihilation operator. Majorana fermions can be bound to a defect, and then combined objects are called Majorana bound states, or zero modes, and you can analyze them in terms of anyons, the way they will move around one another. And people have thought about building topological quantum computers based on them, a little of which I've talked to you about. And then there are quantum vortices and relations with the fractional quantum Hall effect. I just mentioned this to show you that this and references to the different parts of this are not hard to find. You can just go on Google and say Majorana fermion, go to the Wikipedia, and then out, and there's all sorts of things that you can look at. And this is a little more. The team from the Kavli Institute of Nanoscience at Delft in the Netherlands reported a couple of years ago an experiment involving nanowires where that dream of Kitaev about getting correlations by having the Majorana fermions in adjacent electrons interacting with one another. They claim to have seen some of the predicted results of that in their experiment, and there have been some other experiments as well. For example, these guys have used scanning electron microscope methods and have seen some evidence of the Majorana fermions. So it's not that electrons are actually decomposed into two other particles. Probably you'll never see them come apart, but something is going on there that little mathematical hint was showing us, the little hint of A plus IB. Right, here's another example. And another diagram from a paper, Cooper pairing, as I said. And another one. So it's active. And I think maybe it looks a little slow to me on the experimental side, in that I didn't see people reproducing the Delft experiment from my reading of papers on the internet, but something is happening here. I wanted to tell you about the mathematical side. So here's the situation. This is very pretty. I take a row of Majorana fermions, right? So that just means I have Clifford algebra, right? Each one squared is equal to 1, and they anti-commute with one another. Just that, all right? And I think of them as a little row of particles. And then you define these operators, 1 plus AI plus 1 times AI divided by root 2, or 1 minus AI plus 1 times AI divided by root 2. Those are inverses to one another in the algebra. And then you find that they satisfy the braiding operations. Now, I'd better give you that so you see, and maybe it's on the slide. I can avoid drawing on the board. By braiding equation, I mean this. You'll have 3 strands, and you twist the first 2. Then you twist the second 2, and then you twist the first 2. And you get a line which goes all the way over the top of the other 2, and the other 2 are crossing down there. So you can take this line that's going over these and push it downward, and take that little crossing and push it upward, and it'll end up over here, which means you twist the second 2, and then you twist the first 2, and then you twist the second 2. So that's the basic, that's the fundamental relation in braiding. And the braids form a group, because if you have something like this, a braid, you can take another one and put it immediately underneath it and attach the top strands of one to the bottom strands of the other, and multiply them in that way.
Would a crystal lattice be your row?
I'm sorry?
In a crystal lattice where you have a row of electrons that could do this?
Yeah.
So that's something you could look for a lot.
You could have, in a crystal lattice, you could have rows of electrons, or in these nanowires, they have rows of electrons. So you might think of this as temporal picture, or you can think of it as a spatial picture. You don't have to think of it as the world line of electrons or particles moving around one another. You can just think of it as a strand. And then I make braids by weaving them, just like I would with hair, but weaving lines together. And this is a basic relation in the braid group, ABA equals BAB, or sigma 1, sigma 2, sigma 1 equals sigma 2, sigma 1, sigma 2. And the fact of the matter is that rows of Majorana fermions produce, in a completely natural way, braiding operators. The simplest instance of this is the quaternions. And I point out to you how the quaternions arise out of a Clifford algebra with three guys, A, B, and C, three Majorana fermions. You form BA, CB, and AC. And each one squares to -1. And if you take I times J, you'll get K. If you take J times K, you get I, and if you take I, you get J. If you take I times J times K, you get -1. You produce the quaternions immediately out of them by taking the pair products, which have square -1, and putting them in the right order. Just try it for yourself. Take BA times CB. Well, A and C anti-commute, so I have to bring B past C, and that causes a sign change. And then I take B past A, and it gives another sign change, two sign changes. So BACB is BBAC, but BB is 1, so I get AC, which is K. So IJ is K. You get the quaternions out of the Majoranas, out of the Clifford. Of course, you can get the Clifford out of the quaternions as well. So like Peter likes to start with algebras that are fundamentally quaternion, and you can build all these other algebras out of them if you want. It's just a choice. I like the Clifford ones because they're related to the discrete process and the square root of -1 in the way that I was telling you. Anyway, if you now form these three quaternion operators, 1 plus I, 1 plus J, and 1 plus K, you will find that they braid one another. They do the braiding. And this is the general case. But then there's a second way in which this works. On the one hand, you have the row of Majorana fermions. I've got a more readable notation here. And these are the braiding operators. All right, what I said before. But now I'm going to let them act on the vector space whose basis is the fermions themselves. So that's a way of talking about letting it act on the fermions themselves, the Majorana fermions. And I act by conjugation. Tau kx, tau k inverse is the way it acts. If you do that, this is perhaps Ivanov's invention, then you find that it's very simple. T applied to an x, two adjacent x and y. T applied to an x is a y, the next one. And T applied to the y is minus the x. And that's the bit of braiding. And this corresponds, for a pair of fermions, to the well-known belt trick, which is often done this way, but I'm doing it where I interchange two particles. So I have no twist on the string, and I interchange them without turning, and I end up with 360 degrees of twist on the string. All right? You may have done this before inadvertently if you hadn't done it consciously, right? So if you just have a belt and you just do that, you get a 360-degree twist happening. But when you just take the pure belt trick, you don't know whether that phase, if you think that that twist in the belt is a phase, you don't know whether it belongs to this one or this one. It belongs to them both. It's not associated with the left one or the right one. But in this algebra, a choice has been made, and one by the conjugation, in fact. Excuse me. I chose to conjugate that way, tau k x, tau k inverse. If I'd done it the other way around, inverse x, tau k, it would have chosen it the other way. There's a left-right choice in making that, and that choice causes one of them to get the twist and the other one doesn't get the twist. So, so there's a little more than just the bare topology in this, and that's the braid. It's very simple. They interchange, and one of them gets a minus sign, and when they're farther apart, they don't get acted on at all. Now that doesn't look like much, but it's enough, actually. It's strong enough to produce operators which can produce enough braiding so you can do some quantum computing. You have to add on a few other one-dimensional operators in order to do it, but it's very interesting and fundamental. If you have a bunch of these Marjorana fermions, then they give rise to this braiding. It's there. It would be there if they were there. And so that's the story about the braiding. A very slim little thing, but sometimes slim little things can have a big effect.
Is there any experimental confirmation?
What?
Is there any experimental confirmation for this braiding?
I doubt it. It's been hard enough for these people to manage to just see the kind of correlation effects that they would expect. So to get to the braiding would be even harder. The same is true of what I told you about before in relation to the quantum Hall effect and those collectivities of electrons that have phases that go around in the theory. Again, I don't think that there's any experimental confirmation in the offing for either of these things. But they're there in the theory. And if one could, and so it's very tantalizing to see whether one could eventually have experiments that show them in practice.
The quantum computer would perhaps
and that quantum computer that's based on this or the other one is obviously way off in the future. But why are people interested in this topological thing? Well, just because it's topology. You see, if something is topological, it means that if you perturb it a bit, it won't change very much within some level of perturbation. If the thing circles out a long ways around and gets a phase, or it circles nearby and gets a phase, it'll still be the same thing. So up to some perturbations, things should be the same. So one hopes that it's a guard against the problems of decoherence, but it's not clear, except that it is clear that it's fascinating. And maybe that's enough to keep one trying to do research on it.
One more question. Why are you using the word quantum? Why do you keep using the word quantum in this? It seems to me you're
I don't know. It
studying
keeps creeping into my talk, doesn't it?
because the entities are, I mean, it's really the topology of these entities, and the entities could be quantum objects,
Right.
could be anything.
Well, let me say a word about that, my attitude about quantum, because I know you have some particular thoughts about quantum that may be different from mine. But my training has me describe quantum in the following way: that there's a certain framework, and if I'm using that framework, then I'm looking at things quantum, or I'm working in a quantum way. And that framework is that I'm here in a laboratory or a real-world situation, and there are some things that I can observe. And it may be that the right way to handle what I observe is to say, okay, I have a list of all the things that I can observe, and I will just make them the basis of a vector space, or orthonormal to one another. I mean, symbols for them, yes? And then I will look at physical states that are combinations of those possible observations. There is the model of observation, which is obviously a mathematician's construction, and it is. It's von Neumann's idea. That you would model observation by simply projecting out into one of those possibilities. And the probability of getting that observation is the absolute square of the coefficient of the state vector. And that's quantum mechanics. Physical processes preserve the probability distribution that's given implicitly by those complex
I don't know
numbers.
that that's exclusively. Probably you just said are not
Well, I didn't say exclusively. Quantum processes are those processes which preserve that distribution.
Well, they're classical.
And who's to say that that model is everything? That model turns out to work very well in a lot of situations. But and it's so simple to describe mathematically that it's hard to believe that it describes everything, right? Of course, we left out lots of physical considerations, energy and so on. But I don't think there's any reason to assume that the quantum description is anything other than a remarkably successful method of getting some results. That's my
It must be distinguished from classical somehow.
Yeah.
The question is how, and whether that how pertains here. I think the how is actually goes back to the beginning. The Hamiltonian conjugate variables are non-commuting in quantum mechanics. They're commuting in classical physics.
Yes.
So there are actually only two venues where you have this property. One is phase space, and the other is in squeeze space for waves, phase and amplitude. Everything else is non-quantum. The polarization, for example, in electrodynamics was actually worked out by Stokes, 70, 80 years before we have a quantum mechanics. So you can't start using experiments with polarization to plumb quantum effects.
Well, it's a very nice seductive situation, right? Because you know, and have evolved procedures for rewriting every single classical thing in terms of a quantum operator, and you know how to do these translations, and you get good results out of all of this. And it's very difficult to find any other way to get those good results. So, yeah. We should talk some more outside this.
I think Stokes got good results.
Well, I keep the word quantum. When I do use the word quantum, that's the sense in which
I think you're restricting yourself. This is the topology of these objects, and the objects have certain properties which are shared by some classical objects that are not in phase space or not in squeeze space. It's much more general than quantum. Quantum is a very
but as he was saying, the question is, he said, well, has anybody observed these braidings?
Yeah.
All right, well, that's the real question, right? How could you observe the braiding?
That's a real question, yeah.
Right. That's a real question, right? How could you observe that braiding?
Yeah.
Probably at the present time, observing that braiding
with microscopic objects it might be.
Would involve inventing or discovering new experimental techniques and thinking in the quantum way, because that's what we have.
If you want to observe it with microscopic objects, maybe, but maybe you can take a string like you just did and exhibit something totally macroscopic and illustrate the same thing.
Yeah.
Because it's a topological thing, and you were just pointing out that topology is not metrically dependent.
We'll talk some more about this. Let me go on here. So now I want to talk about the Dirac equation now, and show some things. So I'm going to proceed in a more or less classical way, but you'll see that I will end up tunneling my way over to here. You'll see. So let's start with E squared equals P squared plus M squared, where I choose my speed of light equal to 1 and so on. And remind ourselves that you can get a square root of that a la Dirac. I'm going to be in one dimension of space and one dimension of time for a long time. So I'll choose alpha and beta to form that little Clifford algebra we were working with before. Alpha squared equals beta squared equals 1, and alpha beta plus beta alpha equals 0. And then E squared, if I were to write it formally like that, will be equal to P squared plus M squared. So that's Dirac's idea. And then if you combine that with, pardon the phrase, quantum mechanics, we associate Where's that pointer? It always disappears. There. We associate with the energy operator I d by dt, and with the momentum, the operator minus I d by dx. Remember, I set them it's equal to physical constants equal to 1. So then energy equals alpha p plus beta m becomes I d psi dt equals minus I alpha d psi dx plus beta m psi. That's the Dirac equation in 1, and the Dirac operator is this guy here. Because I put it all on one side of the equation. I just put it all equal to 0. Okay, so that became plus, this became minus, and there's the Dirac equation. Okay. And then here's a plane wave to test with, and I apply O to the plane wave, and I don't get 0. I pull down the E, I pull down a minus alpha p and a minus beta m. You probably shouldn't worry about the signs too much. I sometimes get them wrong also. Times the plane wave. So let's call that delta. Now, suppose you multiply delta by beta alpha. Well, then it turns into beta alpha E plus beta P plus alpha M. And if you call that U, you will notice that its equal is now equal to 0. We arrived at a nilpotent. Because alpha delta beta alpha psi brings one more delta down, and I get U squared and it's equal to 0. So you see, if I take psi equal to beta alpha U, where times EVI px minus ET, that'll be a solution to the Dirac equation. So that suggests that, excuse me, I just repeated it here, but it suggests that if I rewrite the Dirac operator by multiplying it by beta alpha, then I will have d psi equals u psi, and that means that that u psi is the solution to the Dirac equation. The Dirac operator, the new one, creates the solution, and then the solution proceeds to make it the solution. So we have this, that d of u times the plane wave is u squared is equal to 0, and so u itself is the guts of this solution to the Dirac equation, and that's essentially the same as Peter's nilpotent solution. All I've done is tell a story where I start with the usual Dirac equation and walk my way over to his formulation. And if you would like to re-put it in terms of quaternions, it will be easy for you to do that. I've left it in my nilpotent but Clifford algebra form. So, I found this intriguing to do because then I can sit with a physics book and look at the way they do the Dirac equation and make a comparison. And then, what can we do with this? Well, I'm interested in thinking, as Peter pointed out in his book, that you could think of the U as various things. You can think of it as the fermion, but you can also think of it as the fermion operator. I mean, it's a spin operator that we manufactured this way, but why not think of it as the fermion operator that corresponds to the one that we were imagining from quantum field theory at the very beginning, right? The one that was square 0 and its conjugate was square 0 and it had the right commutation relation and all that. Well, in that case, we need to decide what's the conjugate operator. And one way to decide on a conjugate operator, and I think there's more than one that you can play with, would be to reverse the time, all right? So that would be the time reversed particle or the antiparticle. So I put a plus in here, and I apply d to that, and see what I get, and I get u, what I'll call u conjugate. Well, what did I do? I changed the sign on e. That's all I did. I left p and m alone and changed the sign on e. So I wonder if I wrote this on the slide. But you will find then that u squared and u dagger squared are both 0, and that there's the anti-commutation relation. In this case, it's unnormalized, but it gives you 4e squared. So we're getting a nice picture of the fermion operator situation coming directly out of the Dirac equation. Okay? Let's take this further and find the Marjorana operators and see what happens. So, so how do I find the Marjorana operators? Well, I want A and B such that U is A plus I. Oh, I see. Sorry, because it came out squared, I could have made a better slide. But let me say what I'm after. Here we have U and we have U dagger. So we're looking for A and B, so that U is A plus IB, and U dagger is A minus IB. So of course, that says that A is equal to U plus U dagger divided by 2, and that B is equal to U minus U dagger divided by 2I. So I can always get these guys from these guys, and it's easy enough to see that these then satisfy up to a constant or something the Clifford algebra that I wanted. That's just going back and forth between them. The correct commutation relation here gives the Clifford algebra over here. So so if we had the U that you're looking at, so alpha beta E plus beta P minus alpha beta E plus beta P minus alpha M. And the U dagger was in fact minus beta, was in fact, oh, it was beta. Beta. Minus beta. Minus alpha. And that's what happened when we reverse the time. So you see what happens if I take U plus U dagger. Then the E's cancel out, and I collect up the P's together, and I get beta P minus alpha M. That's what I get. And if I take the other one, I get U minus U dagger divided by 2I. Then this cancels, and I get beta alpha E over I. And that's a nice combination because it will square to 1 as it should. But you see what happened is that that when you form the Marjorana operators out of this, one of them picked up P and M, and the other one picked up E. Right? And if we had decided, instead of taking the reversal of time, if we had decided to take the reversal of space, then this one would have gotten a minus sign, and we would have picked up something different. We would have gotten a different combination than the one that I showed you. So, so I thought I made a slide of it. I did, right. So for time reversal, one operator had an E and the other one had P and M. For spin reversal, for the space direction reversal, I would get P and the E and M together, and if I reverse them both, then I will get E and P together and M separately. Curious, but I get different Marjorana decompositions depending on what conjugate I have in mind, which indicates that the decomposition into the Marjorana operators is not is at the very least dependent on some extra structure in the physics. It isn't just somehow God-given one way to do it and only one way to do it. And also, it would have to be, well, I don't know what else to say, but that's what I get out of this, and I thought it was interesting to report on this to you. So, whoops, that we can look at the fermion operators that come naturally out of the Dirac equation via the nilpotent construction, and then look at decomposition into Clifford algebra or Majorana operators that come from it, and you get a kind of nice answer. And can you do something with that physically? I don't know. But that's the answer. Okay. If you write in full Dirac algebra, you end up turning the momentum operator into 3 variables, of course, and then you need to dot in that to take those with coefficients in some other algebra, and Peter would take the dual quaternion algebra, and here I'm being completely classical, so I just take the Pauli algebra, but I assume that it commutes with the other algebra that I wrote. And then you can do everything that I did before and write it out. But now comes another thing that's interesting to look at, and that'll be the end of this part of the discussion. The other thing that's interesting to look at is what Majorana himself did. Majorana himself, I didn't tell you about that. He wrote this nice paper. You can get it on the web, in fact. He wrote it back in the 1930s, but it's not hard to find it. He thought, well, I'm looking for particles that are their own antiparticles. So why don't I rewrite the Dirac equation in such a way that it's entirely real, and the complex numbers have been abolished? Could I do that? Well, I have these Dirac matrices to play with, and they have eyes in them, and if I could combine them in the right way, then the eyes could all disappear, and I would have this matrix differential equation that didn't have any eyes in it. And that would be a real Dirac equation, and I'll think about it. And that's what he did in his paper. And if you were to say it in this Clifford algebra way, it amounts to this, that you have the 3 directions of momentum here, and you have 2 copies of this little Clifford algebra, all right? I will call epsilon and eta. I will call epsilon and eta one of them, and the other one epsilon hat and eta hat. Sorry, that's unreadable notation. But then you need a bit of Clifford algebra multiplying everybody, and I have slipped the I all the way across the equation and out, and written out what amounts to the Dirac equation, the standard one. And you'll notice that this is a product of 2 matrices, which have no eyes in them, and so is this, and so is this, and so is that. And they all have the right anti-commuting properties to be a set of matrices for the Dirac equation. I've written it in this condensed way, but the thing about it is that it isn't just one algebra outside of the other algebra in the momentum part. And I don't know how to do it that way. It might be you could. The way Peter was writing the Dirac equation, and the way I indicated just a moment ago, to write the Dirac equation in the usual form, you have one algebra that commutes with the other algebra, and it's entirely working in the dx, dy, dz. And then you have the other algebra on the outside. So they're nicely split apart from one another. Here they're mixed up with one another. And if you're trying to solve the crossword puzzle of making this work and be real, you seem to run into the problem that you can't do that. You have to let them mix. And that's interesting, and I bring it up because I would like to discuss with Peter and anybody else who's interested in this whether or not it's forced that way, and what it would mean in Peter's cosmology for the algebras to mix that way. It's not against his cosmology, it's just something that maybe has to happen. I won't bother you with checking that this is indeed the Dirac equation, because this is very technical detail to play around with this a little bit. But that's the story about that. And also, the other thing that I keep trying to do, but I'm not sure I succeed, is I would like to keep thinking of these as processes, going back to the iterates at the beginning, and think of these as discrete processes mixed with continuous differentiations. But I'm not sure that's the right thing to do at this point.
10 minutes if you will.
We're now almost done. Let me let me bring it to a conclusion. And first of all, you can think of Feynman's checkerboard for a few more fermions, and the usual Feynman checkerboard has this as the Dirac equation written in light cone coordinates and has the I in it. And then these paths in the Feynman checkerboard, which form the propagator for the Dirac equation, are sums over paths with I to the number of corners in the path. And that's where the I happens in the usual Dirac equation when you're in 1 plus 1. But there's another solution to the Dirac equation in 1 plus 1, which is the real one. So here's a real solution, the real differential equation in the simplest possible form. So this is the simplest Marjorana form. That's amusing. And that means that, that means that we would have, I thought I had a picture of paths. No, but it's the same paths in the light cone, in light cone coordinates. And you just sum to -1 to the number of corners instead of I to the number of corners. And you get the Dirac equation, and that's an example of honest, real Dirac equation. So it may be possible to extend that notion into 3 dimensions, or 2 plus 1 dimensions. And then a wider and more general view, getting back to the beginning about distinction, is certainly this, that the universal equation should be about the state of the universe. And an operator should act on the universe to produce nothing. But the universe is both an operator and something that is operated upon. So we should take the universe to be the operator, and then you get the universal nilpotent equation, u squared is equal to 0, which the Dirac equation is one of the first special cases. But while that sounds like nonsense, it isn't quite nonsense, right? Because it is going back to this situation where there is some distinction that is going to be made that creates a reality, creates a universe, creates a distinction, and that distinction, in a certain sense, out of its very nature, produces this nilpotency. So the nilpotency that we're seeing happening, like seemingly by a trick, when you watched it happen with the Dirac equation, starting from the usual situation, is really not a trick. It's really fundamental, and I think that Peter's right in bringing it forth as the fundamental thing, and that the other kind of picture of Dirac that I was drawing is somehow secondary. We should tell the story in that way, which it does. And of course, another simple example is just Spencer Brown's mark itself as the operator, which will give you the simplest nilpotent that I know. And that again is not quite nonsense. That's going back to what are the properties of awareness distinction happening right now. It's a nilpotent operator. So in this formalism, the mark makes the distinction. We've said this before. And the physical theory could be, I should say, seen to write itself in terms of the condition for observation to occur at all. Ideally, that's the way you want the physical theory to appear. Like that.
So, what are your future plans? What do you advise your children and grandchildren to get into?
Well, I'm not professionally a physicist, so I work on topological problems with graduate students. And occasionally, someone comes along who's interested in physics, and I talk to them. But I'm not in the perhaps more dangerous position of a physicist who is sending people out with epistemologies that don't coincide with the rest of their community. But that's a problem, is it not? I mean, you might say, I agree with this kind of thinking, but then what should I tell students? Because after all, they have to have careers. I mean, I think it's worth discussing, because what that says is somehow if we believe that these points of view are not just mine, other points of view that come up here are fundamental, but we worry that they would wreck people's careers, then somehow you have to stop worrying and really believe in your ideas.
Easier said than done, though.
Yeah, I know.
Again, I'd like to go back to social semiotics. It says that everything is sign. We think it's sign, and signs are triadic. Irreversibly, sign refers to determined sign. Sign determines interpretation, which is, I think, model, in such a way that the model is correspond to the object. So my perspective,
You're saying there should be a correct interlock between sign, symbol, and interpreter.
yes,
Yeah.
they
Right.
three forms, they categories.
As Peirce would have said to us, right?
Yeah. Now-
And indeed it must be so, but how often do we think about it when we're either doing pure mathematical problem or some physical
I think
problem?
unless we do that, we cannot communicate. It's there.
Yeah.
It's in us. Now, so my question is this. Just as you have done with the zero totality theory is a model of reality. Just you can describe elegantly the reality in terms of zero totality formalism. Why can't we replace zero with infinity? Infinite possibility.
Why can't we explain zero with infinity?
Yes. Why can't you explain reality in terms of infinite set of possibilities?
Put back in my account.
Now you say zero,
Can I sign and date?
but we don't know what the reality
There's
is.
an infinite number of
I'm
zeros.
sorry.
Excuse me, I know the answer to this. There's an infinite number
Yeah,
of
that's my
zeros.
grandson said.
So that's really what it's about. It's about zero repeating itself infinitely.
That's a possibility.
Yeah, no, that's what it is.
The infinite possibility would include that possibility
I
too.
won't disagree.
So my impression is that I think there are many ways of describing reality. Zero totality is one, but there are other
Okay,
ways.
so we can notice this. There may be many ways of describing reality, but what physicists are engaged in are describing and creating eigenforms that interlock in a repeatable way.
Yes.
And it's entirely possible that the whole enterprise is just designed to work, and that it doesn't describe any reality at all.
Well, I wouldn't say that. I think reality, unless
the reality.
it's grounded in
Well, I don't wanna go
reality,
there.
I don't think you see such a consistent regularity. Because the reality may be rational and regular.
The point is that it is science, right? If you go out there and you discover things like electromagnetism or other phenomena, and though you never would have imagined them. You didn't make them up out of just applying some idea to itself again and again.
Those haven't been
But then in order to work with it, you then are in this arena of repeatability and eigenform and getting everything to fit. And so you're constrained in that because that's the only way you know how to proceed.
Yeah, I use the cookie cutter paradigm. It's the mundane expression. But, there are so many different cookie cutters. If you use certain cookie cutters, you are adopting certain framework within which you can strengthen.
Well, this isn't what's happening. This is saying, this is what we're faced with. As Lou says, we found electromagnetism, there's nothing we can do about it. We didn't say we wanted electromagnetism, that's what we got. And he's saying that's the same with this. This is what we got, and this is what we've got to put up with.
That's a one way. Sure, that's an important aspect of reality.
You might say it would be nice if it was like this, but it can well isn't. And you've got to do what it is like. I'm sorry, but can we have another question? We can discuss it.
I think you have to make a connection to the physical world. The ordinary number system, now that's very useful because it just counts things and you find things in nature that you can count. And so that has a direct connection in a way. It's our way of handling the model.
Yeah, sure.
And now you've got this quantum area, but you've got to find connections to the real world. And I don't think that you've shown that.
Well, no, it wasn't my purpose to show any new connections to the real world, but I told you about some that are in the offing, right? I mean, let's take Dirac's equation. Dirac does a mathematical thing. He says, well, I could take a formal square root of the energy by using a Clifford algebra, and I could write an equation that's analogous to the Schrodinger equation, and that would be very pretty. But then it turned out that it was more than pretty. It actually described things that people could observe. Right? Now, I'm not walking in here and showing you something brand new and something what would be nice, something brand new in physics that comes from mathematics that would be like the Dirac equation. I'm actually just reformulating things you already know, and I told you a story about how people are finding this little bit of mathematics about the Marjorana fermions very suggestive, and people are following it out, and maybe they're going to find out that that actually indicates that there really are phenomena there, right? The other things that I'm saying are almost tautological, I believe. I'm saying that there's a structure to the way we observe and distinguish that is interwoven with our physics and our mathematics, and we should pay attention to it. And I've articulated some aspects of that in relation to some known physics and some known mathematics. I don't think I can fault myself, except it would be better if I could come forth and come to you and say, and here is the replacement for the Dirac equation or something, but I don't have to.
They like open up and have the same